remember what we have. We have a space of, not space, a set of all disks in a plane. Particular disk D is at X, Y is the center, radius R. This is sent to something which is in Minkowski space. Maybe I'll put like this, Minkowski space, 1, 3, with the quadratic form. Means like you know how to measure the length, right? And that's how you do. This X dot is X over R, Y over R. So they are reduced coordinates of that circle. This is simply curvature. And this one we last time explained, this is co-curvature. And this thing is that if you remember a unit disk, if you have your disk in question, like this one, if you invert it through this disk with a new one, curvature of this, we'll call it co-curvature of this one. And we proved why that's true, right? Another thing about this, the norm of this stuff is 1. So x squared plus, well, actually minus, okay, minus plus beta gamma is -1, right? The question to you, I'm using x dot y dot for these reduced coordinates. Can you find, because you want to really distinguish between x and y here and x and y here as in the Minkowski space. So I thought maybe just call it bold x, bold y, because this dot is maybe a little bothering for a second, right? So maybe in writing, I'll make bold x, bold y, and this is not bold x, bold y. Maybe that would be better. And another thing is that many people prefer this. And that will be one. That's also fine. And I don't know which one to choose. But as a physicist, I prefer space to be right and so on. Now the thing is that you can get out of this a symbol. I'll call it a symbol. Just write that vector in this format. This is the same thing, right? Just put it differently. And reduced symbol would be x dot y dot over beta. So from this we get that, but we can write it that way. Okay? So this is the symbol. This is an element of space-time, as I told you. But because of that, all disks end up with points or maybe like vectors on the hyperbolic. So this is what we covered until now. And you can watch this video just to see some details, okay? What about, so we call this map mu. You can say it ascending from plane to 4-dimensional space-time to the universe. Do we have an inverse map? Yes, because from this, let me put it here, mu to -1. It will go to x and y. Center is simply x dot over beta and y dot over beta. So this, you can read off the coordinates directly from the symbol, right? And then what about radius? It will be just 1 over beta. So that's the inverse map, okay? So this is what we know, and we know a little more, maybe, but what else do we know? Let me see. Maybe recalling some information. The dot product between this is disk A and B. We represent it by a vector in space-time, so I'll be using, again, A and B for these two things. But anyway, in Minkowski space, this dot product, determined by this, which we talked about, is always 1 if they are tangent. And it doesn't matter on their sizes, right? And that's how beauty of it. Now, A with itself is just norm of A squared is -1. So they are on the thing, right? Another thing we need to know, maybe this. If they are perpendicular to each other, so here the angle is right, then A and B is 0. This is what we know from the previous meetings. Okay, now let's go ahead. So as I told you, there's this famous quadratic equation associated to Descartes and a number of other people. And we try to live without it for quite a while. And then our proof will be much simpler using this mu than the one provided in typical literature. But let's see how much we can get just for that map, okay? So, already this and this and this. So number one, how do you construct an Apollonian basket, okay? So maybe see this. This is, let's say, A, and another this B, right? They're going like around. Let's say this is C. You want to complete this to 4 disks which are mutually tangent. And as you remember, there are 2 solutions. Where's the first solution? Obviously here, right? It's tangent to all of
That's the second.
This is second solution. What is the third solution? Okay, what's the first solution? This one. That's the solution. Okay. So this one is D and this is D prime, or vice versa. You're the expert.
I forgot.
So it doesn't matter, right? They're really symmetric. It will show, or maybe a few more examples. The example we started with, remember, this was the question of Descartes to the Prince Elizabeth of Bohemia. Find the radius of the small one, which is tangent to the 3. And then he didn't notice there are 2 solutions. This is one, and that's another one. So this is just the same thing, but slightly rearranged. Should we see another maybe example? Yeah, what about this? This is one disk, which happens to be half a plane. Remember, circle, when you straighten it, it's still a circle, and then half plane would be a disk. It's infinite disk. Here's another one, tangent to it, but at infinity. And here is a circle, a disk. So 3 of them. Where is the 4th one tangent simultaneously to both of them? Here or here, right? So such 2 disks, with respect to given A, B, C, which are tangent to each other, they will be called, let's call them conjugate disks with respect to A, B, and C, okay? And here is our first sort of theorem, okay? D as a vector, so this thing, D plus D prime, it is twice A plus B plus C. So first let's prove it, and then we'll use it to construct whatever you want, including window. So proof, so this is like theorem, proof. You wouldn't believe how trivial is this. Okay.
Sorry. It wouldn't work.
So the proof is the following. D prime, this would mean that this is 2A plus 2B plus 2C minus D. Imagine that you have to do it like in coordinates, right? Using, I don't know, Pythagorean theorem 100 times or something like this. You just write this. Now, we show 3 things. One, that the norm of this is -1. What it will show you that this probably represents a disk. So we'll calculate it later. I'll start with simple calculations. Number 2, maybe that D, also this is prime, sorry, prime, right? D with A, the inner product. Yeah, this one we'll calculate. D is 2A plus 2B plus 2C minus D, and with A. Now, of course, this is a regular inner product. You can distribute it. So we'll get 2A with A plus 2B with A, inner product, plus 2C with A, inner product, minus D with A. Now let's calculate, let's evaluate it. A with A is the same thing. This is -1. So we have -2. B with A, they are tangent, right? So A, yeah, okay, tangent. So this would be +2. These are tangent plus another 2, and DA are tangent, -1. So what is it? To make 1. What does it mean? This new disk, which we don't know yet what it is definitely tangent to A. See, this D prime is tangent to A. Just showed it. Well, very similar way, it is tangent to B and to C. Calculations are the same. And now, maybe then this is just simply D. For some reason, it's nothing new. Well, calculate B would actually maybe, that would be good to calculate now. Sorry. But I'm skipping it because if we just this by the same, you'll get a lot of terms, all they beautifully reduce and then like next to trivial. Simple. And I would suggest let's calculate maybe D prime with D. So I leave it to you, okay? And the number is, what's the holy number of among numbers on this planet? 7, of course, right?
I
So,
thought it was 42.
no, there's the meaning.
That's true. But it's-
7 is the magic.
Yeah,
So
that's-
you can show this, so this is number 3. And this means it cannot be the same thing. All right. So we have this is a beautiful tool now to do a lot of stuff. And let us maybe now do exercises, okay? Yeah.
You bring us crayons?
The crayons will be distributed in a second. And
Don't get
we'll
sprayed.
talk after we talk.
No dissing crayons, you like them.
Can I ask you a thing?
Absolutely.
It's might be video, but you are doing, you know,
Yes.
B, for B and A, right?
Mhm.
So, and B and A are orthogonal, right? So.
D and A are not orthogonal. D is here.
B and A.
Oh, B and A, they're tangent. We're starting with okay, we're starting maybe this A, B, C. They're mutually tangent. Now we're looking for one which is simultaneous tangent to this, and to this. And the claim is that if you find one, there will be another one. Let's say this is D. If you find one, the claim is okay, there is another one you missed. And then we just only prove that if you add D plus D prime as two vectors, that will be that. And we prove it by, okay, resolving this into D prime and showing that D prime is also a this and so on.
Yeah, so because I was wondering how did that inner product become 1? Because I was thinking it was 0. Because I was thinking orthogonal, so I
That would
was.
be strange. That would be strange. This is D prime A. D prime A, the new one. You want to
The
show
outside
this?
one, the
Yes,
outside one.
yes. So you want to show this still. Okay,
Thank you.
all right. So let's have fun with actually using it for something.
I'm sorry, so the 7 one is the outer one with the small little one, inner one, right?
Yes, yes. So we show that this is truly not the same thing, because if this was the same thing, I mean,
So, yeah.
in principle, we don't know what we got here, right? It is just tangent to 3 of them, we already have one, maybe this is the same one. But we show no, because this with this won't give you -1, it's a truly. Okay, so, take your crayons out, Leonard. You came unprepared always.
Now we're gonna have a hard time.
Nice crayon. Okay, so the thing is, let's start with this. This is like very simply constructed. Here's a, let's say, X and Y. It is in the center, and this circle has curvature because it goes outside -1. Okay. Now, what's curvature of this one? We're trying to like fill the numbers. Let's talk only about curvatures. By the way, do you see this? This thing here is x dot, y dot, beta, and gamma. Same thing here, same thing here, same thing here. This is just algebraic simple expression, right? This means it is true for only curvature, or only x's, or only y's independently. Each of them. So let's take care only of curvatures first. I suggest to put here maybe just below the line. What's the curvature of this one? Well, this is at half, right? And radius is also half, therefore. So the curvature will be 2, the reciprocal of the thing. What's the curvature of this?
Which one did you find?
This one.
Well, by symmetry, I would hope it would be 2.
2. Okay. 2, 2, negative 1. Now we need the new ones.
Okay.
By symmetry, they're the same. So if this is x, then this is x. So what we can write? These are conjugated disks with respect to the 3. This is the solution. Given those 3, where is the next one tangent to them? Here and here. So x plus x, I'll help you because I know this is half step. You might have forgotten everything you learned in grammar school. So x plus x would be equal twice 2 plus 2 minus 1, right? No calculator. What is x?
Okay, good.
What
Well,
is
else said
6?
the same number.
3,
This is 6.
I would hope.
that's 6, but that's 2x, that's why it's 3.
3. Okay, so this is 3 and by symmetry 3. Okay. I didn't give you one? Oh. Okay, so guys, what about this one? I'll take a minute and think about this. Let's call it now a new x, right?
Is that going to be 4?
No guessing, no guessing.
Okay, that was a
So
total.
it's tangent to 3 and
You have to first identify who solution to what it is and what will be the other solution. Can you find here 3 disks it is tangent to?
2. It's tangent to 3 and 2. I got 4.
Yes. Here
And here, yes.
and the external one.
Yeah. No, the outside one I did not take.
Yeah, it's going outside.
Yeah.
Okay. Now we need to find also the other solution to those 3. This which is tangent to this, and to this simultaneously. Let's make it dotted. Where is the other dotted? Conjugated. You have only 30 minutes. Where's the other planet?
So you're wanting to know what's tangent to
To those 3.
those 3?
This is 1, this is 2, of course, the whole thing, and this is the third.
So
This is 1.
4.
But where is first the disk? Where is the other disk which is tangent to this, and to this? Maybe. This one?
Down. Yeah.
This is tangent to this, but
No,
and to
not
this,
that one.
but not to this. Oh,
Which
oops.
is the 2.
Well, I can see 10 to 3 of them.
It's not totally true, guys.
No,
I'm not wasting
right.
time
You're
then.
right, of course.
Yeah,
Well, it touches that, and
But this 3 and this 3 are the same.
Yeah, but just physically, where is the, you know,
What are
the,
the 2? It's the other 2.
yes.
Oh, see, I was going between the 3 and the 2. Okay.
Everybody can see this. This is the dual, or let's say conjugate disk. So this is like a solution to the card problem, right? For the Elizabeth. So this is Elizabethan disk, and this is the other Elizabethan. Oh, that's a good name, the disk. So we know that x plus 2 would be the sum of the three. Put twice, 2 times 3 plus 2 minus 1, am I right? 3, 2 minus 1. This is one solution, this is the other solution, that's it. Okay, now your job, what is x?
I got the
You
other
read this
side.
time. 6. What do you have?
I got this side.
You're claiming 6?
Well, that's
You're risking 6?
8. Yeah, I'm
Do you
risking
dare? Thank you. If it's a color by number, you wouldn't want to use the wrong color.
Yeah,
It would ruin the
with the
picture.
crayons, you could use different colors.
Yes.
So,
Well,
yes,
You'd need a lot
it
of
is
colors.
6. So we can put here 6.
Very fine.
Because of the symmetry, this is another 6, another 6, another 6, right? I was thinking maybe to force you to just do one more to really start to, like, have a good feeling for it. I don't know, which one do you want to calculate? Yeah, let's calculate this one. Yeah, let's do this.
understand how that 2 was tangent.
Okay, so right, do we
The other
have,
one in the
do we have like a
previous
3 that are clearly tangent to this? Well, this one,
Right, those are.
this
easy.
one, and this one.
Right, those.
Where is its dual?
That's the question I was having. Then that's why I'm saying I gotta understand how you had that being tangent before the dual.
Something which is tangent simultaneously to this, and to outsider.
Does that
So that
constantly progress
three-
like that?
Hmm?
Does it constantly progress like that?
That.
Yeah, huge.
Oh, so that you thought that too?
Okay.
This.
You think it's that bottom 3?
No, it could be the 3, right? 6, 2, negative 1, it could go.
Oh, yes,
That is
good,
beautiful.
good.
Okay, so
So
we
this is
both,
But pays for her.
It equals
Absence.
2 times, x plus 3 equals 2 times, then 6 plus 2 minus 1. So x plus 3 is
You got it?
2,
What is it?
8 minus
11.
1,
And then,
15 minus 3, yes, 11. Yeah.
and then we can write first. And do you see how it works? So you can slowly, if you have like 3 many vacations, you can go with those numbers forever. Okay. Is there anything like pattern here showing up?
Very quickly.
Yeah, let's talk about patterns in a second. But anyway, you can feel it, okay, and you can force a computer actually to do this job, right? Here is actually, yeah, maybe I'll give you now. These are the numbers already in. But don't
Okay.
look on other pages, only the first page.
oh, okay.
If I catch you,
Oh, no.
only first page.
I don't open it and all the evils will fly out. There's
Only
no hope
for-
at the bottom of this.
Well, hey, this is forbidden, only first page.
Yeah, and if we open it up, all the evils will fly out.
Yeah,
And
that's
there's no
right.
hope at the bottom.
This is Pandora hangout. Okay, guys. Now, what about the positions? Suppose you will have a computer, you would like to draw it, so you have to know the full information about every disk. So the curvature is not enough. Where the hell is the center? So put a little maybe line above each of these guys, and we'll construct symbols. Right? So symbols for this one. So do you remember at the top we have to put x and dot here, x dot and y dot. What is x dot? It is a position divided by radius, right? So what is x on this point? Half divided by radius, which is half. This is 1. Half divided by half. You're shocked. It's 1. It always is. What about the y? Y is 0. If you divide it, it's still 0. So what about here?
-1.
-1, because it will be negative half of the position divided by half of the radius. And y is still 0, this is clear. This one's a little tougher, but not really, because what's the position here? Well, this is 1, and this radius is 1/3. So this will be 2/3. 2/3 divided by 1/3, it will be 2.
On the other one, yeah.
What about x? 0. So this one will be 0, -2, and so on. So you see how it works? You can construct all of them in this just one simple way. Okay. So you see, very powerful, huh? Yeah, let's talk now about maybe some, because once you feel it, you start to see some structures, okay, in it. So I'll maybe put this one will be easier than the one to put there.
Does this have anything to do with, when they were talking about non-Euclidean, geometry with the circles going along the belt?
Oh, yeah. Actually, it does.
Okay, oh,
Yeah, maybe first let's, today is like, how do you call it? Entertainment mathematics or recreational mathematics. You see here at the bottom, there are those numbers, it's not this. Our thing is better. Ours is better. But notice here, like for instance, this is what you're talking about. There's so-called Pappus of Alexandria.
yeah.
I'll put like this way. Like, what was it, like second century, like 200?
And wasn't he said something, carbon.
He came up with a beautiful theorem, and I have no idea how he did it without inversive geometry. But he noticed the following thing. If you start with a line, cut it any place you want. Now make your semicircle, make your corresponding semicircle, and semicircle on this whole thing. Okay, this shape here is called arbelos, if you remember from ancient geometry. Now let's fill here those circles inside. So this is perhaps you remember. This is called Pappus chain. It's a chain of circles. And he noticed one funny thing, that pick up any of them, like this one. The height here, hi, because this is I equals 0, I equal 1, so the first and so on. This is, let's say, n. So this is hn, and the diameter is dn. So he showed that hn is just n times this diameter. Isn't it amazing? So, challenge, prove it. But anyway, so this is called Pappus chain. We have here a Pappus chain. Because you can think, okay, this is our first one, you see on the right side. This is, or maybe from this side, okay? This is one. This is the next one. This is the next one. This is the next one, okay? So the progression of those things. Oh, did we get these numbers here? No, but I'll tell you that this is 3 and 4. We'll calculate it the same way, okay? And this one for 11, it is 8 and 6. But we don't need it, well, maybe. For Pappus chain, So what's diameter of this one? Well, radius is 1/6, so that diameter will be 1/3. And this is exactly 1/3 is just two of these 1/3 because the height is 2/3. So it works for this one, right? Special case. But look at just curvatures here. What's the progression of curvatures? 2, 3, 6, 11. Okay. And then before 2, it will be another 2. Do you see this goes actually around? Just goes around. Okay, can you guess the next number? Just look at that. This is one of those IQ tests.
Five.
What's the
1,
next
2,
number?
5.
18.
Right.
Yeah, I looked at it.
Yeah, because we go, I stopped in because you're going up.
But what's the rule?
27,
The
27
prime.
is the next one.
Hmm?
27 is the next one, right?
27, right? You cheated
That's
too?
no. 9. Is that right?
Yeah, I think so.
Yeah, right?
Okay, my rule was wrong.
11 plus 11. 27 plus
Subtract 2. Subtract 2. You get 0, 1, 4,
Yeah, then
9, 16,
1, 5.
25.
Yeah.
The squares.
Yeah, okay.
So this is the first maybe kind of nice thing we found. Okay. What else? Do you see here? If you look only at the guys at the boundary, we have just very few of them. Very few of them. But notice 3 and 4 is a like Pythagorean triangle, 3, 4, and the hypotenuse will be 5, right? 6 minus 1. 8 and 6, hypotenuse will be 10. Here, cheating, I don't remember what, but they form Pythagorean triples. So we have Pythagorean triples. Actually, all of them are here. It's just amazing. Yeah, we just wonder. So we'll come to this. It's a very important actually fact. What else? Okay, so now take this away. That was just for fun. But I want to look at this way. That this chain is squeezed between two discs. You see, you have two discs, this one, and the chain is just squeezed between the two discs. So why don't we have like define a generalized Pappus chain? And we won't even use the word generalized. And this is like any chain when you have like, I don't know, like for instance, here, that would be something squeezed between two. Or any other situation, I don't know. This is just the same drawing. This is Pappus chain, and this is just a very special case, but they have to be tangent. This is tangent to this, okay? Now, what would be the equation for such a thing? Okay, so this is number 2. Okay, so claim, so theorem. So let's call it C1. You can start one, this C2, C3, and so on. This is A and B. So claim is that Cn plus 1 is the same thing as twice the previous minus previous to the previous plus 2A plus B. So all those chains, wherever you do them, they satisfy this. Now, these are vectors. So this means true for curvatures, true for x dots, for y dots, for gammas. So you see, this is beautiful. We're getting all of them together. Now, how would you guys prove it? The proof is very simple. when you look at any of them, let's say this one, you see? So this is Cn. No, I'll have to draw a little better. Yeah, maybe this one is better. This is Cn. This is Cn plus 1 or minus 1, but then this will be Cn minus 1. So notice that this circle is tangent to this and to this. That's your triple of disks. It has two solutions. This is a solution, this is a solution. So this means that using our theorem, the previous one, Cn minus 1 plus Cn plus 1, right? This and this, these are conjugated. It will be just the sum of the three. Cn plus A plus B taken twice. And suddenly we know how to produce those chains. Isn't it absolutely beautiful? There's such a simple proofs coming from this. And typically people would try to solve. I mean, actually nobody talks about this chain. All right, what else? Oh, we have just 10 minutes maybe. So I'll just go to a very important implication of our first, which I raised, right? The first claim. May I raise it, by the way? So let's introduce now something which is known in literature as Apollonian group. Okay. So what is it? Notice that, what was it? Like, let's point it here. D prime, a new D conjugated to this one would be twice A plus 2B plus 2C minus D. Remember this? And yeah, I don't have to draw the picture again, right? Remember? Okay, can you use it to fill all these things in like sort of on automatic way? So notice that we did the following thing. This is let's talk only about curvatures, okay? Only curvatures. So the new curvature is this. This is one, this is D, and this will be D prime. This is A, B, C. So really from A, B, C, D, the whole quadruple can give you A, B, C, D prime. How would you calculate it? Well, let's put a matrix here. A, B, C, D. And now what matrix it should be? A, and then how to get A? By 1, 0, 0, 0, right? If you multiply, it will be A. B would be 0, 1, 0, 0. What about C? 0, 0, 1, 0. What about D prime? Two of this, 2, 2, 2, 2, 2 minus. But we change what was D? D. We change D into D prime. But you can change A into A prime, right? Either of them. So if you change A into A prime, you'll get like a little thing there. You know, well, I'll leave it to you to see how it goes. But definitely there are 4 ways you can go. So maybe let's draw it. You can go 4 ways. And then again, 4 ways. And then again, 4 ways and so on. You get a fractal of the paths. So there should be a group pushing you this. This is one element. This is for D prime. How do you change A? I mean, same thing up to D. You want to change this into A prime and B, C, D. What should be your matrix? A, B, C, D. Well, A prime changes now. It will be what? Minus 1, 2, 2, 2, because now B, C, D are the ones which are tangent to A, and then A prime will be calculated according to this formula. So that would be this, and then the other guys stay. You do the same thing for B and for C, okay? So you have four matrices, and those matrices are generators of the something what we call Apollonian group, okay? Is generated by then N1, N2, N3, and N4, and each of them is defined. N1 is on the first place is -1, 2, 2, 2, and then ones, right? N2 is in the second place, 2, -1, 2, 2, and then ones. And M3 and M4, which we have here. Okay, so this is the group. Interesting thing, each of them, if you square it, what do you think you get? Yeah, identity. So it's generated by four elements which square to one identity. Okay, and this is what has been studied by Lagarius and other people, although they got this differently. How did they get it? Well, they got it from Descartes' formula, which we try to ignore for as long as possible, which was something like this. Remember, for 3 circles, or 4 circles, I just don't want to hide anything from you, okay? Twice a squared plus b squared plus c squared plus d squared. Remember, your homework was calculate d out of this. D should show up as a plus b plus c plus minus square root of a b plus b c plus ca. That's what we calculate to true, but we don't accept it because we didn't prove it. And then notice that d prime, so this is d1 and d2, right? 2 solutions. If you add them, these are just curvatures. If you add them, then these guys will get subtracted and you get twice a, twice b, twice c. So you see, but we got that thing directly from the map into the Minkowski space. So it's much easier. And this is only curvatures. So we have to, okay. For people kind of inclined to more abstract stuff, this is one of the so-called thin groups. There is an article on it, on so-called thin groups. And I can put it later on, okay? But that's it. So, computer. Oh, just a second, but right, you can computerize it easily, this group, and look at all possible paths for starting 4, which are already tangent, and get all of them and populate. And remember, this is true not only for curvatures, but each number independently. Maybe 1, how do you calculate that 3 here? Will be 0 plus 1 plus, and so on, right? I mean, so you know how to do it.